Welcome to my dear friends and learners. So, this is a requested video. So, I'll be giving one very brief idea about uh, the practical approach to criticality. So, before to start with the actual measurement or the procedure, let us just recall or refresh the uh, how the geometry of the core is important and how to predict it based on the material, the fuel enrichment and the uh, mass and the volume of the fissile material. So, as we all know, the reactor design starts with the Fick's law. It's basically this will explain the neutron diffusion, which is given by the neutron current density J. I'm not going in deep mathematics, so if someone interested to solve of detail solving methodology of this diffusion equation, then for that I will make separate video. It's a very interesting mathematics that using that you can design uh, a reactor with specific geometry, but you should be very uh, convergent with calculus. Then only this can be conceptualized and better understanding can be achieved. So the neutron current density is basically given by this, where d is the diffusion coefficient and this is the uh, negative concentration gradient. Okay, this symbol is basically the first order differential operator, where phi denotes the neutron flux. Now, the rate of inefficient, the rate of change of a neutron, that is del n by del t with respect to time. Basically, it will. This is the production, the new neutron produced, minus the absorption. This is the this is the macroscopic cross section, and the leakage. So basically, leakage is the leakage term is given by this, which is a divergent of J. Hmm. Now, here in this place, already we know the diffusion equation, which is given by minus uh, d uh, dj by d phi by dx. So this, if you replace this, that means if J is replaced by minus d divergent J, so this term is converted like this, which is basically this is the Laplace operator. Basically, it's a second order differential operator in Euclidean space, and this production term is given by uh, then it is how many, this is basically the uh, neutron, which is basically this term is infinite multiplication factor. You know all these things, so I need not to detail much more this. And now if I rearrange the equation, so this will become like this. Okay. Now I'll do slight mathematical uh, modification. So this entire equation is divided by d phi. It is coming like this, and finally the form is like this. Okay. Then I am bringing all the terms, this all the terms one side. Okay. So by rearranging, it is like this. And as you know, this is basically, this is, as I told, this is the Laplace operator, or the second order differential operator. So in Euclidean space, so that is basically depends on the volume. Okay. So this term is called the geometric buckling, and as this is entirely depend on the fuel material property. Okay. So this part is called, this part is called, this term is called material buckling. So now for the criticality, how much neutron is, because the neutron flux is maintained. Okay. There is no change, there is no rate of change of neutron, number of neutrons in successive. How much consumed, the same is getting produced. Hmm. So that's why this dn for criticality, this is the condition for the criticality. So this dn by dt should be 0, and this terms, it will be cancelled out. This will be 0, and your geometric buckling should be equal to the uh, material buckling. And this is the very common, we know, is the very common statement that for the criticality of a nuclear reactor, the geometric buckling should be equal to the material buckling. Okay. Now if I rewrite that things again, so this is like this, and by rearranging this cross multiplication and taking things here, it is coming like this. This term basically is called, so this part, if you take, and if I define that term is probability of non-leakage for the neutron. So this, I'm defining one more constant, which is effective multiplication factor. Basically that is the product of infinite multiplication factor into the non-leakage probability of the neutron. So from this, as it's a probability, and you know, the probability always, any probability in the world, it will be less than equal to 1. So definitely in practical case, it will be less than 1. So if it is less than 1, and that product should be 1, so definitely this k infinity always should be higher than 1. Okay. This k infinity practically, I mean, when you are calculating, it should be designing the reactor, this should be greater than 1, because otherwise if you consider this equal to 1 or less than 1, then this the reactor will be uh, subcritical, reactor will be subcritical design. Okay. So definitely this k infinity will be greater than 1, and to make a reactor critical, basically you have to, based on the geometry and the material, you have to find all those parameters, and there are a lot of relevance with this parameter with several factors. So you have to design based on the historic or the available data, and after that practically you have to measure the multiplication factor which will once you measure grossly, if you measure in from the practical scenario, then all the effect of this macroscopic cross section, the diffusion coefficient, this buckling, everything, it will be included in the physical measurement. So we are trying to uh, understand that how it is done practically. Okay, so basically from the neutron Fick's law and the neutron diffusion equation, we are for criticality, we are considering the neutron growth is constant. Okay, so there is no change of rate of change of neutron in the reactor core with respect to time. That time means the reactor is critical. With that, we are getting uh, volume, the volume of the reactor core, and we know the enrichment and the density. So based on that, we are calculating how much mass is. So based on this calculation, whatever the reactor volume you are defining, okay, estimating or calculating, that is called the critical volume. And the material, the fuel density and the enrichment, if you know from this volume, you can calculate the mass for this particular volume, which is called critical mass. So criticality is very simple. It's not a very big thing. That if you are able to calculate the critical volume for a particular geometry, and if the enrichment or the the fuel density is the fissile material density is known to you, then you can calculate the critical mass. And if that critical mass is kept inside the critical volume, and there is a neutron initiator, okay, then automatically the chain reaction will sustain. It's very simple. There is no it's by virtue, the inherent property of the fissile material, it will work, and nothing difficult or complicated. Okay, but as there are several factors are there, this controllability, all these things, the role of delayed neutron, that already I have discussed. Okay, so uh, from this Fick's law and diffusion, by solving the diffusion equation, you are finding the critical mass and critical volume, and based on that, the fuel subassembly is manufactured and how many subassemblies is required to how many subassemblies are to be accumulated to uh, mitigate the critical mass, which will be kept in the critical volume based on the geometric buckling. And then if there is a neutron source or neutron initiator, so it will, the chain reaction will sustain. So if there is a small another assumption or the another statement you should remember, if there is a large volume of, if the reactor volume is very large, so the background neutron, once you are accumulating the more number of fuel subassembly together to to mitigate the critical mass, then the background neutron itself sufficient to start the reactor. But if the reactor core size is very small, then the background neutron count is not sufficient, then you need to introduce some external neutron source to kickstart the reactor. Okay, so exactly what I was telling. So in practical, so to control the reactor, you know there is a control and absorber rod driving mechanism. By once the absorber rod is in the extreme down position, so the maximum neutrons are getting absorbed, and neutron population in the core is not sufficient enough to proceed with the fission. Okay, so we can tell, so for, and also the this effective multiplication factor. So finally I can write that this is a function of number of subassembly loaded in the core as well as the observer rod position. Okay, so from this discussion, what we will, before um, going for the criticality, we need to verify, because based on the design value already, number of subassembly required for go for the criticality, it is designed and calculated. This is to be verified. Okay, so using some methodology, we need to find out that number of subassembly required to achieve the k effective 1 without observer rod. That means if that many numbers of subassemblies are uh, loaded in the core and there is no observer rod, then that background neutron population will increase eventually, and that neutron itself sufficient enough to maintain the sustainable chain reaction, which implies the effective multiplication factor is 1. So the first thing we will estimate that. Okay, how many number of subassemblies required in the core which will take the reactor towards criticality. The next thing is the observer or position, because we need to control the power and we need to shut down. All these things are required. So the observer, the position of the observer rod, and how the effective multiplication factor is varying up based on the observer rod position, even though the critical mass is kept in critical volume. Okay, so once the observer rod is extreme down, so the maximum number of neutron is absorbed and fission is not started, and slowly once you are lifting the observer rod, the neutron population is increasing. Okay, and once it is reached at a particular value, then the sustainable chain reaction will continue. Here slide mathematics. Say I am introducing n number of neutron in the so this calculation is without control rod, or the control rod taken extreme up. Okay, we want to verify how many numbers of subassembly required in the core to go for criticality. So say s number of neutron is introduced in the reactor core, then based on the whatever may be the effective multiplication factor, so this will go like this, continue. In the next generation, it will go like this, and so on. So now if you see, at a finite number of generation which is extremely large, so the total number of neutron population in the core is like this red box total. So if you take s common, then 1 plus k effective square, k effective cube, and so on. It will be an infinite series. So an infinite series of common ratio k effective. So the summation will be 1 by 1 minus r. Okay, it's a infinite GP series. So that is basically s into 1 by 1 minus k effective. So this term we are defining this 1 minus k effective, we are defining as inverse multiplication factor, or 1 by m. Basically we are going to estimate this for both the cases. Number one, when the control rod is at extreme uh, 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 up extreme position, it is completely lifted, and uh, also the relevance with control rod position. As I was telling, in a large volume of fuel, the background neutron population are more, and it increases eventually by accumulating more number of subassembly in the reactor core. Hence, for sustainable chain reaction is possible if sufficient number of subassembly are loaded in the reactor core, which implies effective multiplication factor is 1. Okay. Now let us slightly do some mathematical exercise. Say if I number of subassembly loaded in the reactor core produces neutron flux phi I, and the effective multiplication factor is k effective I, and j number of subassembly loaded in the reactor core produces neutron flux phi j, and the effective multiplication factor k effective j. Okay, so I number of subassembly accumulates S counts due to its background neutron population, and J number of subassembly accumulates Sj count due to its background neutron population. So now this can be written so from the above from the earlier from this this can be written the neutron flux, which is proportional to the neutron count, which we are measuring from the uh, uh, neutron detector, some constant into for ith for for I number of subassembly if it is loaded. So this is given by this, and if j number of subassembly loaded, it is given by this. Okay, it's very simple. Now we need to find out we have to estimate to plot the curve. We need to estimate several constant which we are introduced in the previous equation. Okay, so now say there is a known batch of subassembly initially loaded in the core. Okay, and it is compared to the total subassembly required in the to go for the criticality, the initial batch of subassembly loaded in the core are significantly small. Okay, and in such case we can nullify the effect of multiplication factor. Okay, because it is, as I told, this very the first batch of loading will be very small. Okay, so if for I number of subassembly is accumulating Si number of neutrons, then we can write Si is equal to some constant into I. That means the number of subassembly loaded in the core, background neutron will increase proportionally. Okay, so during the initial loading, the known batch of subassembly, say I is equal to n, is loaded in the core, and the background count is measured Sn. Then I can write this from this equation, and your k is equal to Sn by n. And now this equation can be rewrite as Si is equal to Sn by n into I, where Sn and n is obtained from the initial batch of loading. Okay. Now I am rewriting the earlier equation that your in place of Si, I am putting these things and your Ai is like this. With the same condition, a known batch of subassembly, suppose I is equal to n is loaded in the core, and I am introducing one source of count is 0, which produces the neutron flux phi 0, and the equivalent count is neutron count is A0, which is monitored in the neutron detector. Don't be confused, because it's simply to calculating all this constant for more accuracy. So this is a simple variation problem. So your Ai is equal to, this is the equation, initial equation, and the A0 from this statement I am replacing this A0 is equal to zeta S0 by this one, and we considered that uh, as the very less number of subassembly loaded, so fission will not take place, because the effective multiplication factor is tends to 0. Then this equation is turned to this, and from there you are finding the value of zeta. Okay. Now in the finally I am replacing this zeta is like this, simple mathematics. And now the final equation, which is turned that if I number of these are the these from this exercise, earlier the exercise what I explained, from there these values are known, and now if you vary the number of subassembly, which is I am defining this term as mi, and this is the neutron count monitor in the neutron detector. Now if you vary the number of subassembly loaded in the core, you can find a relationship between mi and I. Okay, so it is looks like that it's something like rectangular hyperbola kind of graph you will obtain. So now from this equation what we will do, I load each batch of subassembly and I will find out the value of m. But here we should be very, because all the cases we are lifting the absorber rod completely, so we cannot go for extreme, because that time automatically the reactor will critical. So we should stop, say, up to when the value of K effective is 0.5 or 0.6, like that. Okay. So now this is the plot, whatever we understand. So say that your x-axis is number of subassembly loaded in the core. So up to this dotted line left hand side. So from here we started the minimum number of subassembly loaded in the core, and this y-axis is the m, value of m. Okay, and up to say this value is 0.5 tak we plotted for each batch of subassembly loaded in the core. After that, these things we cannot, after that it is not advisable to lift completely the observer rod and measure the value. So after that, with this segment of the graph we extrapolated and taken the line where it is touches the x-axis. So touches the x-axis means their m is equal to 0. M0 means m is equal to basically 1 minus k effective. Correct. So M0 means your K effective is 1. That means your criticality is achieved. So with this experiment, we can estimate by extrapolating the curve that how many subassemblies are required to go for the criticality. And this is verified with the design value that the first job is done. The second thing is, now once the number of subassembly required for the critically is extrapolated as explained in the earlier and verified with the design value, then drop down the absorber rod fully and load the intended number of uh, fuel subassembly in the reactor core. This will ensure that core is uh, the core of critical volume is loaded with critical mass of fuel. Okay, now if we lift the absorber rod and if we know the absorber rod position at which the effective multiplication factor will go to will tends to 1, that means your reactor will critical and the chain reaction will sustain. So the neutron population due to large number of fuel volume are sufficient to move the core towards criticality by withdrawing the absorber rod. Say when the absorber rod is fully inserted, the count is, because there will be some count A0 and the source strength is, we know the source strength because number of subassembly, how much subassembly we loaded, we know, and this all Sn and N we already estimated from the earlier experiment. So and number of subassembly loaded also, you know. So the total source strength SC is given by like this. Okay, now if you put A0 and as the absorber rod is completely brought down, then the effective multiplication factor also can be neglected and we can write this A0 is equal to zeta into this and this, and from there zeta is basically A0 by SC one way. Now if I substitute, then this my A delta, that is the neutron count for a particular absorber rod position, is this into this, and I can again substituting writing these things as m delta. Now here from here you can see this will give the relationship at every steps of absorber rod withdrawn. You measure the neutron count and those will give basically the measurement of inverse multiplication factor at that particular absorber rod position. And the same way you plot this curve also plotted like this, and up to after a certain value you should be restricted to withdraw the absorber rod further, and from here it is extrapolated, and where the uh, uh, extrapolated line will cut the x-axis, that is the, so here this is the control rod position and this is the inverse multiplication factor. So the position where the uh, this extrapolated curve is exactly cut the x-axis, that is the position of the control rod absorber rod when the criticality will be obtained. Now once you know that, then you prepare all the prerequisite of the reactors to go for the criticality, and slowly lift the absorber rod up to the value which we have estimated by the extrapolation. Then automatically your reactor will go for the criticality. So this is the very conceptual thing I have shared. I have not given any particular data related to this, because those are supposed not to revealed. In general procedure, where this is the textbook concept I have shared among you for your better understanding. So hope it will be useful for you. Thank you so much. Thanks for your patience.